Okay, today we're going to go through this October 2021 paper from Unit 2 of Pearson Edexcel International A-Level Physics exam. So it's very similar to the linear exam used by Edexcel, except these are modular. So this module is normally taken in June, and my students are preparing for this module as we speak, so this will allow them to have another practice exam and then see how their answers are different to the way that I've done them, using the mark scheme, but also showing the model answers is a bit clearer than just reading the mark scheme. Okay, as usual, last week I did an exam for the January 24 module exam on Unit 4 for students who may need to retake that. So I'm trying to do some for the Year 13 students and some for the Year 12 students, and this will be the next exam for Year 12 students. And your grade in Year 12 is basically 40% from Unit 1, 40% from Unit 2, and 20% from Unit 3. Unit 3 is practical skills. So this first question we're going through is to do with a thermistor. Yeah, it's to do with a filament lamp. Previous exam we had one which is thermistor. So the graph shows how potential difference varies with current for an electrical component. Now normally when they give you, these are called voltage current characteristics, they normally put the independent variable, which is the voltage, on the x-axis and current on the y-axis. So they've done it the other way around, so don't get confused, because when you're doing this in class, it's normal to have the variables the other way around. So I think that's why I got confused with thermistor, because one of my students had put this down as a thermistor in a previous year group. Okay, so this is not a thermistor, and it's a filament lamp. So we know it's not a diode because a diode shape is completely different. You need to know the characteristics of an ohmic conductor, like a wire or a fixed resistor. So ohmic would be fixed resistor, and that's only as long as the temperature is controlled, or a length of wire. Okay. The filament lamp, it varies, the voltage controls the temperature, so you can't actually control the temperature. So as the voltage goes up, the resistance increases due to the lattice vibrations. Okay, so this is the shape. So in this, because they've changed the voltage current axes around, this time as resistance is equal to voltage divided by current, in this case the steepness does show you that as it's getting steeper, the resistance voltage to current ratio is higher. So it is the filament lamp. If it was thermistor, the thermistor graph would look like this if the voltage and current were on the other axes. Hope that makes sense. Okay. Okay, question 2 at the bottom of this same page is about the wavelength of light emitted by a laser. So a student determines the wavelength of light emitted by a laser. So this is the formula that you need to use, n lambda equals d sine theta, which is on your exam sheet list of equations or formulae. She uses the laser, a diffraction grating, and a screen. Okay, so this is a core practical, so you need to make sure you know the details, the method, and how the results are analyzed. So basically, the diffraction grating has a value of d that you need to be able to work out. Yeah, and they want to know which of the following measurements is not required. Okay, well, the distance from the laser to diffraction grating is not required. So basically you have the laser light going in, you've got a diffraction grating there, and it has loads of slits, and the number of slits allows you to work out the distance between the slits, which is what d is. It then produces light on a screen, yeah, a certain distance, I usually call it the big D, away from the thing. So the distance you need is the distance from the big screen. The reason you need it is because the central part of the light will produce a bright fringe, and then you got n number, so n equals 1 will be here, n equals 0 is the center one, n equals 1 will be on both sides, n equals 2 will be a different angle, and you can work out, so n equals 2 will also be here, So that's the order of the bright fringes. So you do not need the distance between the laser, which will be here, say, and the diffraction grating. So the answer is C. You do need the distance from the diffraction grating to the screen because you need it to be able to work out theta. You need the distance from the central maxima to the first order because that allows you to work out the theta using trigonometry. Yeah? So you got this distance, and this distance allows you to work out the theta that you need to put in the equation. And obviously you need the distance between the slits because this is D, okay? And that's given to you with the diffraction grating calculation. They tell you how many slits there are per millimeter, so that's a calculation that you need to be able to do. So only C is not required. The next question is question 3, which is the equation which is also given to you, I equals NQVA. It relates the current in a sample of material to the movement of free charge carriers in the sample. Okay? So you basically need to know what each of these letters stands for. Which of the following is a correct definition of one of the terms in this equation? So first of all, they're giving you N for an A. N represents the number of charge carriers in the sample. Well, it's not quite. It's the number of charge carriers per meter cubed. It's not the total number of charge carriers because it depends on the sample size. So N is a value per meter cubed. Q represents a total charge stored in the sample. No. Q is the charge of each of the charge carriers. So in this case, it would normally be an electron. So Q normally is equal to E, which is equal to 1.6 times 10 to the power of minus 19, and of course if it's an electron it would be negative. Okay. V represents drift velocity of the charge carriers in the sample. That's correct. It's how they are drifting towards the positive if they're electrons. Okay. And A represents the surface area. No, it's not the surface area, it's the cross-sectional area of the sample. Okay. So this is some basic stuff that they want you to know. This is all knowledge-based. The beginning of the multiple choice normally starts with just checking that you have a decent knowledge of physics. Okay. The temperature of a thermistor is increased. Which row in the table identifies the effect of temperature increase on the number of conduction electrons and the amplitude of the lattice vibrations? Okay. So the number of conduction electrons will increase with a thermistor, yeah, because a thermistor is called a negative temperature coefficient, has a negative temperature coefficient, which means as you increase the temperature, the resistance decreases. And the reason that happens is because as you increase temperature, you actually free up more electrons and they become conduction electrons before they were bound by their atoms. So it has to be A or C. And then C, it says if you increase temperature, the amplitude of lattice vibration stays the same. Well, that's not true. Okay, so it has to be A or C, because that's what happens with a negative temperature coefficient material, like a thermistor, that you need to know for your exam. So the only answer is, the possibility is A. Okay, so this is how you get to do multiple choice questions, is you need to make sure you can eliminate some of the answers quite quickly. Now it then gives you a unit of resistance is the ohm, so the formula for the ohm is given from voltage over current. That means if we're looking at the units, we need to find out which of the following is equivalent to the ohm. An ohm would be joules per coulomb, because a volt is a joule per coulomb, so JC to the minus 1. And you can see all of the answers have joules in it. You don't have to do it in base units. Current is coulombs per second. They just want you to see that you can mess around with the units and to simplify them. So it's joules per coulomb divided by coulombs per second, which comes out to joules coulombs to the minus 2 times seconds, which is the only answer is A. It's just being able to combine units. A very useful thing to be able to do in this exam in physics. Okay, so the next question is another core practical. Yeah. So these are a very good way. We've now had 2 core practicals in the multiple choice questions. So hopefully you've carried out this experiment yourselves. Core practical means that you will need to know the full procedure of the methods and how you analyze the data. Okay, so let's just read the top. The speed of waves on a vibrating string. So here we have a vibrating string under tension, is investigated using the apparatus as shown. So you've got a vibrator. So it's a vibration generator, which is connected to a a signal generator. So frequency generator. So you can adjust the frequency of the vibrator. And at certain frequencies, you'll get what's called a standing wave setup. Okay, so basically frequencies that cause maximum amplitude on the string. Okay, and you increase, you can adjust the tension using the hanging masses. Okay, the equation therefore is V equals square root of the tension divided by mu, where mu is the mass per unit length of the string. So it depends on the density, if you like, of the string. The other equation you need is the wave equation. So once we know those, we can then look at what the question's asking. Okay? Just trying to see if how much of the question and the answers I can get on the screen for you. So the length of the string between the vibrator and the pulley is L. Okay? Now you can see the vibration shown is not a complete wavelength. It's half a wavelength, because if it was a complete wavelength, it would go down, and this is the peak, and it would then create the one with the trough. So it would be the wavelength as drawn, lambda, it would be equal to twice the length shown. Okay, so that's what I put here. The length of the string between the pulley and the masses is given as L over 3. Now we'll come back to this because they want you to use this to be able to work out mu. Okay, or come up with an expression algebraically for mu, and the mass of the whole string is m. Yeah, so if we know that mu is the mass per unit length, then it must be mass divided by the total length, which is L plus L over 3, being the length here, added to L over 3, so it's 4L over 3. So if you change that, then the mu value could be expressed as 3m over 4L. Okay, so once we do that, we then also know that the mass of the hanging masses m leads to knowing the tension in the string. Yeah, so tension obviously is due to m times g. Okay, equals tension. So that's what I've put here. So we know all of this. Now it wants you to work out which of the following expressions represents the speed of the string. Well, remember, speed of the waves on the string. So remember we said the speed of the waves on the string is V equal to the tension divided by the mass per unit length square rooted. So this is the equation that's given to you. This is the equation they want you to be able to analyze. And that means we know that the tension is mg, and we know mu is equal to 3m over 4L. So basically we put in the values from above. This should have a square root sign over it. So once you do that, you can just simplify it. The 4 goes to the top, the L goes to the top because it's a fraction over a fraction, and you'll see the only one is A. Okay, so a bit of algebra to be able to get through that. Okay, obviously in the exam you need to do it quite fast, so you're under exam pressures, but as I'm explaining this question to you, I want to make sure that you understand the steps in solving the problems. There's one thing that you cannot be taught in physics, you have to practice yourself, is problem solving skills. So physics works by first of all understanding the underlying principles or the concepts involved. Once you've got that, you can then rely on the maths to help you. But the third stage is then to use the maths to apply the physics to the problem that you've been given. So problem solving is the third stage of learning physics. So here we have a microwave oven, question 7. It has a source which emits microwaves in all directions into the oven. So this is the whole oven, is the rectangle. The diagram shows the paths of 2 microwave rays, path 1 going to the top, let's call it the top path, which has a length of 30 centimeters, 22 plus 8, and the bottom path to L is 15 plus 27, which is 42 centimeters. So we have two paths, so they have what's called a path difference, and the path difference is 12 centimeters. Okay, so let's see what they're asking. The interference between the waves following these two paths could cause heating effects at L. So we're looking at the effect at L. So in other words, these two waves arriving, are they going to be in phase or out of phase? This is what they're trying to say. So if it would cause heating, that means they would be arriving in phase, depending on the wavelengths of the microwaves. Okay, so they're given us two possible wavelengths of the microwaves in the table. Which row that they give of the table is possible at point L? Okay, so for there to be no heating, they must be out of phase by half a wavelength. Okay, and you can see that 24 is double the path difference. That means that the difference in the path traveled is exactly half a wavelength, and therefore they're going to be out of phase, so it's going to be destructive. Okay, so there's going to be no heating. So this gets 2 ticks. So why can't it be the other one, 18? Well, 18 is 2/3, the path difference is 2/3 of a wavelength apart. And 2/3 is neither in phase nor out of phase, so therefore it's not going to be heating, it's not going to be no heating, and it's not going to be full heating. Okay, so it won't be correct in terms of that. So from these two answers, we know that this one is both correct. So then the only other option would be to see if this one would create maximum heating. No, it wouldn't, because they're half a wavelength out of phase, so it creates no heating, not maximum heating. Okay, so you could actually work out, if it was 18 centimeters, exactly what's happening and what's happening with 24 centimeters. But whenever the path difference is half a wavelength, you get cancellation or destructive interference, which leads to no heating. And whenever it's a full number of wavelengths, the path difference, you will have a cumulative effect of the energies of the two waves. It's a superposition of the waves. It leads to constructive interference. Okay? And if it's 2/3 of a wavelength, you might as well ignore it, because it's neither in phase nor out of phase. Okay, so that's question 7. Question 8 is to do with potential dividers. Okay, so basically this is a cell which has two paths in parallel. You've got an AB, a wire going from A to B, a length of wire X, and then the second path is going through two fixed resistors, R1 and R2. And then looking at the difference in the voltage between the two resistors compared with the difference in voltage at a value of Y across the length of wire. Okay, as you know, the resistance across a length of wire increases with length. So you're basically dividing the resistance of the wire according to two ratios of length, Y, and obviously this would then be X minus Y, because the wire, a current carrying wire AB of length X and uniform diameter, is connected in a circuit as shown. So this is your knowledge that the resistance is equal to the resistivity of the material. That's obviously the wire is made from the same material, times the length divided by the area. And since the area doesn't change and the wire doesn't change, resistance is proportional to length, directly proportional to length. So that's just some background physics that you need to know. Just going to move it slightly up so you can see the 4 choices and my solutions. So we don't need the first sentence. It's just telling us it's a wire of uniform diameter. Now the slider S, this is the slider S. So you can move this slider across, yeah, along the wire until the reading on the voltmeter is 0 volts. Okay, so they're looking for a position where the reading on the voltmeter becomes 0 volts. Okay, now why are they doing that? Because they want you to understand that voltage at any point in a circuit has a certain potential value. Yeah, so it'll have maximum value at this end and 0 value at this end, say. So I always teach to our students the negative, which should be considered 0, and this one be the maximum voltage. Okay, So that's what we're doing. I want to see when does the length here that they put the slider at, when does that length create a voltage or potential at that point which is equal to the potential between the two resistors. Okay, so it's a ratio of resistances. So we know that the resistance on the top is proportional to the length. So R of Y, the resistance of length Y, is equal to K times Y. And the resistance of X minus Y is K times X minus Y, where K is the combination of the resistivity in the cross-sectional area. Okay, so you can then work out that the resistance of these two lengths, Y to X minus Y, must be equal to the resistors underneath, which is R1 to R2, if the potential between the two is the same. Okay, when the voltmeter reads 0, you know the ratio of this to this must be equal to the ratio of this part of the wire to this part of the wire. Okay, so it's a simple matter of ratios. So when you do that, you can cross out the k's, which was k was actually equal to rho over a from the equation I showed you above. Okay, so you don't really need to know that. As long as you know it's the ratio of the lengths is equal to the ratio of the resistances, then you can use the ratios to work out the algebra they're looking for. So if you do that, you'll see that Y, remember the resistance is proportional to the length, so you just can replace Ry with Y, and resistance of X minus Y with X, because as I've shown you, that's what it's equal to. So that's equal to R1 over R2, which gives you the ratio B. Okay? I hope that makes sense. So I know I spent a long time on this one because I know one or two of my students were confused about this theory. Okay. That's question 8. Question 9 is about diffraction and making sure you have a good knowledge of diffraction. So these are 4 scenarios. The wavefront diagrams show consecutive waves. So the wavefront shows the wavelength of the waves. So these waves are shorter, these waves are longer, approaching gaps of different sizes. Okay, so when the wavelength corresponds closely with the spacing of the gap, then it will have more diffraction. When the wavelength is not of a similar size to the gap, then the diffraction is limited. Okay, so that's basically the knowledge you need to have. I've drawn in these are my curves. So I'm showing that this one will be the least curve, B, and that's going to be the answer, because now let's look at the wording. So remember, when we're doing problem solving, we basically want to know what does the examiner expect us to know about this concept in physics. And that's why doing past papers allows you to train yourself into being able to get into the head of the examiner and understanding what exactly they're looking for. So the wavefronts diffract as they pass through each gap, as I've explained. In which diagram will the diffracted waves not be semicircular? Well, you saw my diagrams. The one which is least semicircular is diagram B. Okay? Why is that? Because for A, lambda is approximately equal to the gap, so that's going to be circular, or semicircular. C, lambda also is approximately equal to the gap, as is D, whereas for B, the wavelength is not that equal to the gap. The gap is much larger than the wavelength, and that's why they want you to know that. So if lambda is much smaller than the gap, it will not curve the same amount. It will not produce a semicircular pattern. Okay, that's question 9 done. And now the final question on question 10. I hope you find this useful for your revision. Is on a sound wave. So sound wave travels through air. The diagram represents the displacement of air particles. Okay, so they're looking at the individual particles as they're based on their distance along the wave at a specific instant in time. Okay, so it's like a screenshot, if you like, of the vibration of the particles at that position. So V, they're telling you, is a compression. That means the next 0 amplitude of the displacement being 0 of the air particles will be a rarefaction. Okay, and the one after that will be a compression again. Because remember, for a full wave, it will be the distance between two compressions, which will give you a maxima and a minima. Yeah, you need to have the peak and the trough if you were looking at just the wave motion. So they want you to know at which position is there also a compression. So we know the answer must be Z, and obviously it will be that. So they want to see that you know this information at the centers of compression and the centers of rarefaction. So the areas where the waves come together, they get compressed, the center one isn't actually displaced. And then where they're spread out the most, the center of the rarefaction is also not displaced. It's the ones next to the center ones which get pushed towards the center of compression, and the ones which are pulled away from the center of rarefaction which are displaced the most. The centers, this is important, the centers of compression and rarefaction have a displacement of 0. Okay? Once you know this knowledge, then even a longitudinal wave can be represented by displacement distance graph as shown. Okay, so that's why it gives you the full information you require to be able to answer the question. Okay, let you struggle with that if you are still need to do a bit more revision. Okay, I think this is explained in the International A-level book. Yeah, if you've read the chapter on compressions and rarefactions, you can find it and it will be explained in that section. Okay, that's the end of the multiple choice questions. Okay. And we're going to go through the shorter answers of section B. So section B is where you have to have full written answers. The exam is 1 hour and 20 minutes. So the multiple choice should have only taken 10 minutes of your time. So it's about a minute a mark. So at 1 hour and 30 minutes is the exam. And it's 80 marks. So you get slightly more than 1 minute a mark. But obviously when I'm going through it, I'm explaining it to you. So we're actually having a revision lesson on it. So the first question is on ray diagrams, and it's to do with refraction. So they're using diamonds, cubic zirconia, which are basically fake diamonds, which you can buy in jewelry shops, and silicon carbide. I don't know what that is. They can be used as gemstones in jewelry. So here they are. They're giving you the speed of light in each material. Obviously, the more the speed of light slows down, the more the refractive index must be, because remember that C is 3.00 times 10 to the 8 meters per second. Okay, so that's in a vacuum. Or in air doesn't really slow down very much. Okay, the refractive index in air is 1.00 something. It's you need to go to several decimal places to work out how much air slows it down. So the speed of light is given in the table as shown. In order to identify the materials, a ray of light is directed towards a boundary between the air and the gemstone. So I put the N of the gemstone as Ng, where N of air is 1.00, because the speed of light in air is basically to 2 decimal places, also 3.00. So we can say that the refractive index of air is 1.00. Okay, so when it goes in, this is called the angle of incidence. So I equals 50, and angle of refraction is 21 degrees. Now, if you remember from your GCSE, did use the material you used for the gemstone, because one is air, you can just say the N of the gemstone that they've used is sine of angle 50. Sine of 50, the angle of incidence, divided by sine of R. So my year 10 students have just been doing this as well. So sine of 50 is 2.14. Yeah. And now you've got, so that's one method. So you could probably get a mark for saying that you've worked out the refractive index for question 11. I'm just seeing that you've done that. For mark 1, yes, allow the use, so you're allowed to get this, so this gives you 1 mark. Then you can also work out the value of, through the ratio of the speeds. Okay, this equation is given to you also in your equation sheet, and that gives you a value. If you put this value in that we just worked out, you put this into the equation, so that we put the value that we just calculated into there. We know the speed of in a vacuum, we know the speed of light in a vacuum. We want to work out which is the correct v, so we put v as the subject of the formula. 3.00 divided by our 2.14 gives you an answer of approximately 1.4 times 10 to the 8. Well, which value in the table is closest to that? The value in the table which is closest to that is the one for the cubic zirconia. The others are way off, therefore you get one for doing that and one for choosing the correct answer, being 1.39 was very close. Okay, so that's a 3-mark question on refractive index. Oh, okay, it hasn't finished. It's actually a 9-mark question. So the first part is 3, and then we continue. So then part B says diamonds are cut into different shapes so that they sparkle when light shines on them. The diagram shows a ray of light entering, through the straight edge at right angles, so it doesn't get bent at this interface, and the instant on a boundary between diamond and air. Okay, so it goes through, comes here, and I've drawn this as my worked out angle. I can see that this angle is 40.5. So here we have another right angle triangle. So this must be 90 minus 40.5. Therefore, the angle to the normal, the angle of incidence here must be equal to this angle if it totally internally reflects. Okay? Well, we know that the total internal reflection angle depends on the critical angle for the material, which is 1 over n. Okay, so this is showing entering a diamond. So we know the n value for diamond based on the data they've given us. Okay, so what do they want us to do? So we want to work out if the angle 40.5 is bigger than the critical angle. So add to the diagram to show the path. So this is our final answer. Okay, as it leaves the boundary. Okay. So your answer should include a calculation. So sine c is 1 over n, which is v over c, because n is c over v, therefore 1 over n, which is sine c, is equal to v over c, just swapping the equations round. So this is given to you, this you have to work out. Okay, so I put it this way, so that means we know from the table before that the speed of light in bring the table back for you to see. In a diamond, we need to use this value, 1.24. So once we do that, we put that in, divided by 3.0, we get 0.41 degree, 0.41, which is then sine of minus, that gives you an angle of 24 degrees. So the critical angle is 24 degrees, get a mark for that, and then say since I is the angle 40.5 degrees, as we worked out from similar triangles or alternate angles, we can work out that's much greater than the critical angle. So total internal reflection will occur as the boundary as shown, and that will give you your 3rd or your 4th mark. Okay, one for drawing it, one for working out why it is totally internally reflected. Okay. Then it wants you to explain what would happen to the ray at this boundary if the material used was silicon carbide instead. Well, we'd have to do exactly the same thing. This time we'd have to work out the value for sine c using the equation which is 1 over n, which would be v over c. So it would be 1.15 over 30. Where's the 1.15 come from? The value given for silicon carbide in the table is 1.15. Okay, so once we put in the value for silicon carbide, we see the critical angle will be 23 degrees. Okay, so total internal reflection would still take place. So it's asking explain what would happen to the ray if the material used was carbon dioxide, silicon carbide instead of diamond. So it would still be, instead of 24 degrees is 23 degrees, not much difference. So therefore total explain So silicon, this is working it out. Then the explain bit is there for total internal reflection. You should write it out in full probably, would still take place. And as the angle of incidence shown, 40.5, is greater than the critical angle. Yeah, this must be fully explained, not simply calculated, because when they put explain, they want to make sure you leave no implication in your answer. It must be explicit, so you have to spell it out for the examiner. Okay, as I told my students, imagine the examiner sitting in front of you and he keeps saying, okay, why, but why? Yeah, and you've got to explain to him, because the critical angle is still, the angle is still greater than the critical angle. So what does that mean? That means that total internal reflection will still take place. Okay, so that's 9-point question 11. And we'll do one more question, then I'll upload the video, and I'll do the later questions in a second video. Okay, so this is a lot of reading. So if English isn't your first language, you need to make sure you do what I'm doing, which is called active reading. I underline it as I'm reading, so make sure I've gone in. So I stop when I haven't internalized the information. In an experiment, to determine the speed of sound in air. Okay, so we know we want to determine the speed of sound in air. This is what you should be doing. Okay, I've got that. You tell yourself, a student held a vibrating tuning fork. So a tuning fork is the device in this hand. Yeah, you can have tuning forks of different frequencies above a glass tube. Okay, so the glass tube, and here we got water in it. So this is a resonance effect. Okay, so above a glass tube, and here they've got a diagram of it. You can see it's creating a standing wave. The air column in the tube, so this is the air column. The air column is the length here, length of air column. So you have to make sure you understand every single word in an exam. The air column tube could be adjusted, so you can move this tube up and down to vary the length to match this length with the frequency of the fork. So the tuning fork will have a frequency, and obviously a frequency leads to a wavelength, and the wavelength can match the length to an extent where you create a node here and therefore an antinode here. So it's going to produce a loud sound when the length matches one of the fundamental frequencies that's of the tuning fork. So you can raise it and lower it into the tube of water. Yeah, so the water is what it's bouncing off. When the length of air column was L, so they've adjusted it to create the situation where it's producing an antinode. So antinode means maximum amplitude. Therefore, it's going to make a loud or loudest sound. Okay? And you can do this experiment if you have a tube, some water, and different tuning forks. When this happens, a stationary wave with one node and one antinode was produced. So node here and antinode there. Okay? This is not even half a wavelength. A half a wavelength would reach until it's reached the second antinode. And then it would go down. So this is a quarter of a wavelength. Yeah? So you have to realize this diagram shown, antinode to node here, is equal to a quarter of a wavelength. So it's just write lambda over 4 is the length of the diagram that we've shown here. Okay, was produced as shown. This sound, this caused a sound to be heard because it produced a louder amplitude. Okay, a louder vibration. So now, what are they asking? Explain. So it's another explain. Explain how the stationary wave was formed. Well, so they want you to know what a stationary wave is. Sound waves from the tuning fork. So tuning fork, remember, is held at the top here. Reflect off the water surface. Yeah, so there's one mark. So realizing that the sound reflects off the water surface. And the original transmitted wave, or the transmitted wave, means the original sound wave and the reflected wave interfere with each other. That's what they want you to know. Explain how any stationary wave is formed. In this experiment, it's sound waves and the echo interfering with each other. So that's question 12 at the intro. So you now know the scenario. It wants you to now do the mathematics. So as I said to you, first they want you to know the concept, which you now understand as standing waves. Now they'll let you use your maths. A sound was heard when the length was 19.3 centimeters. In other words, they adjusted the length to 19.3 centimeters. It produced a loud sound at that value. So remember that lambda is 4 times the length, yeah? Because it's only a node to antinode. So if we want a full wavelength, you have the amplitude. So this is our tube side here. So you've got a full antinode. There's the bottom of the water, yeah? Then you got the next antinode. So there's our length of our tube. Then you got the next antinode. That's only half a wavelength. You've got to come back and so on. And then you'll see that the 3/4 of the wavelength is not shown. So this is the echo causing the full effect. They then say that they want you to determine a value for the speed of sound in air. So they want you to find V, and they told you the frequency of the tuning fork F is equal to 440 hertz. So we know the wavelength from L, yes. So once we do that, 4 times L, yeah, remember to change it into meters, 0.193. That's a trick that the examiners use to see which students make silly mistakes. If you change it into meters, you will get the maths, as I've shown you, to be approximately 340 meters per second. Always show the accurate value and then show that it's approximately equal to 340 meters. You have 3 significant figures here, 2 to 3 significant here, so you shouldn't really go more than 3 significant figures in your answer. The next part of the question. The antinode is slightly further away from the water than the end of the glass tube. In other words, the maximum amplitude is slightly above the glass tube that they've used. Explain, let's say another explain. That means you've got to spell out. Explain how this would affect the accuracy of your calculated value above. So how would this affect it? Well, if the L should have been slightly longer, in effect, than what we measured. It was the length of the tube. So L is greater than 19.3 centimeters, slightly greater. So lambda would also be longer. So that once you worked out this, that'll give you mark for that. And since V equals F lambda, then the speed value would be higher than the calculated value above. Yeah? So which is therefore less accurate than thought. So the value we answered wasn't quite accurate if this information is correct. And that's how you get the final 2 marks. So I hope you found that useful. I am definitely taking my time over this, but when you're listening to the answers, you can speed up, slow down the speech. I actually listen to most of my own videos at 1.5 speed because the information goes in actually just as well. So I'd recommend when you're listening back to it, put it on 1.5 speed. And then if you confuse, you basically stop the video at that point, copy out my answers. In my school, you're meant to write out your corrected answers after your own attempt in a different color pen. So we use a purple color pen. So I expect my students to do that, to correct their own so they have a model answer. These are model answers. So if you found it useful, please like and share our videos with your friends so we get more subscribers. And if you subscribe, you'll get notified. I think you've got to press that bell notification. Once you do that, you'll be notified of when future videos will be produced. Okay, so we'll come back to this paper by looking at question 13, which you can already see, so you can actually work on it before I come back with the next video. And the next question is on resistivity and filament lamps and electricity. So I hope you found it useful and hopefully see you in the next video. Okay, bye for now.